Welcome back. And like I said, we're going to be talking about transformations in part two of this lecture. The text that goes along with these slides talks about a couple examples of transformation, and one of them is when you decide to change whether you're measuring temperature in Fahrenheit or Celsius, right? Those are two different ways that we can measure temperature, and we're going to get different numbers most of the time if we use Celsius or Fahrenheit, right? Freezing is 0 if you're in Celsius, but it's 32 if you're in Fahrenheit. And so there are two different ways we can measure our data. And you can imagine having a column of data, a variable, and having it either be measured in Celsius and or in Fahrenheit. And the numbers are going to change depending on which way you measure it. We're going to be talking about some transformations that are maybe a little bit less familiar to you than going from Fahrenheit to Celsius. But it's that same idea where we're going to change what units we're measuring something in. So the first thing that we're going to talk about, or the first type of transformation, is standardization. Standardization is going to allow us to convert a variable so that it has a mean of 0 and a standard deviation of 1, just like something called the standard normal distribution that we'll cover in the future. So, why would we want to transform things this way? We'll talk about that a bit more in a moment. But let's make sure we have a very clear definition of standardization here. It refers standardization, the word, to that conversion process, converting a variable so that it indicates how many standard deviation units each data point is from the mean. In other words, creating a new version, a linear transformation of that variable so that it has a mean of 0 and a standard deviation of 1. So once we accomplish this, we're going to create something called a z-score. This is another term that you should know. A z-score is how we refer to a variable or data point that has been standardized, that's gone through the standardization process. So let's look at an example because this is going to make it hopefully a bit clearer. Returning to that data set of Texas school districts, you can see that here we just have one kernel density plot. In the previous graph that we looked at in part one, we had separated out the traditional schools from the charter school districts. In this case, I'm just putting all of the districts together. So this includes uh, both charter schools and traditional school districts and shows the distribution of the teacher turnover rate. And you can see this is measured on the same scale as before, the percent turnover rate that year. We can convert this variable, we can convert any variable that we have to a z-score by standardization. And when we standardize, we're going to need to relabel the axis or change the units that we're measuring so that the mean is 0 and each unit away from 0 is one standard deviation. So here's what our graph is going to look like once we go through that process of standardization. You can see that now the mean is 0, whereas before our mean was around 20. Now the mean is at 0. And this is the same data, but we've just changed the units. This is sort of like graph 1 being measured in Celsius, graph 2 being measured in Fahrenheit, something like that, except these are units that are a little bit less familiar to you probably than Celsius and Fahrenheit. Here we have the teacher turnover rate as a percentage. Here we have it as a z-score. Um, we can see that a turnover rate of 0 previously, 0% turnover rate, now looks like it's taking on a value around -2. The -2 means that the turnover rate is 2 standard deviations below the mean turnover rate among Texas school districts. Similarly, a value of +2 means that a school district has a turnover rate 2 standard deviations above the mean. A 4 would indicate the district has a turnover rate of 4 standard deviations above the mean within the state. So you can see that we have basically the same shape of distribution in these two figures, although Stata by default is actually going to draw these two graphs slightly differently when we do the transformation, because you can see that it's a little bit taller in this second graph after the standardization than in this first graph. But that's just sort of because of how Stata is by default picking what these axes should be, the x-axis and the y-axis, which I said in our first lecture slides that it's very important to pay attention to the axes. For some reason, Stata is changing a little bit how it's drawing those axes such that the it looks a little bit taller, like I said in the second figure, but this is the exact same distribution. It should have the exact same shape before and after a standardization. The only difference is going to be that the units that we're measuring it in are different. So this x-axis is going to look very different. So that's an example which hopefully helps to create some intuition about what we're talking about when we say z-scores or standardization. Let's give a few more details though. This is a formula for how you actually compute a z-score. You compute the z-score by taking your original value, the percentage teacher turnover, and then you subtract from that the mean. Mu, we said, can be representing the mean, so the average teacher turnover rate in the state. And then after doing this subtraction, you're going to divide by the standard deviation among districts for the teacher turnover rate. So that's the formula for how we create a z-score. Notice that standardizing, like we said, doesn't change the shape of the distribution. It's similar to just relabeling the x-axis on a histogram. And in terms of what this formula actually does, subtracting the mean from x moves the distribution horizontally so that it's centered at 0. In other words, it makes it so that 0 is going to be the mean of the distribution. While dividing by the standard deviation is going to make it so that our units now refer to standard deviations. In other words, making it so that if we go 1 unit away from the mean, we're going to be at a value of 1. So that's what these two operations in the formula are accomplishing and why we use that formula to create a standardized variable. All right. Why would we use standardization? What makes it useful? Well, there's a few different reasons that standardization can be useful, but one is that it can make it easier to make comparisons across different distributions that have similar shapes but different means or standard deviations. So here's a practical example. Let's say we have two students. One of them took the ACT and the other one took the SAT. And these are two common college entrance exams that are used in the US, the ACT and the SAT. But these two exams, even though they're testing a lot of the same types of knowledge, maybe not exactly the same types of knowledge, but similar types of knowledge and skills, they are measured in completely different units. They report their scores on different scales. So, one way, if we're trying to say, well, how do we compare the student who got a 36 on the ACT to a student who got, a 137 on the SAT? How do we compare these two students since their scores are different, but they're being measured on completely different scales? How can we compare them? One thing we could do is we could compute a z-score for each of them with this formula. We just have to know what the average ACT score, the average SAT score is, and then the standard deviation of the two exams. And that would allow us to do something, to be able to say something like, well, maybe student one scored one standard deviation above the mean on this exam, while student two took a different exam but scored 1.5 standard deviations above the mean. And that could give us a rough way to be able to compare the two students who took different exams. Now, that makes the assumption that students who take the SAT are similar to students who take the ACT. In other words, if it turns out that all the smartest students take the SAT and the lower performing students take the ACT, this is going to be a very misleading way to be able to compare. But if it's just sort of random, like certain regions of the country are more likely to take one exam or the other, it's not that students who are more skilled are taking one exam or the other, then that's going to be a pretty decent way to be able to compare those two students. I'll also just note that you could also use percentiles. This is another very common way to try to make comparisons across two different exams like this. So often, if you get your SAT or you get your ACT scores right on that form where it gives you your number, it's also going to tell you what percentile you got. So if student A got the 38 or the 70th percentile on their ACT and the other student got the 90th percentile on their SAT, well, we would already know student 2 probably did better because they were in a higher percentile than student 1. All right. There will be other examples or other examples that I could have given about how standardization could be useful, but just hopefully that helps to give you a little bit of an introduction to this process of standardization, what it is, how it's used, and why it might be useful. Let's talk now about another transformation. This one is maybe a slightly more complicated. It's called a logarithmic transformation. Logarithmic transformations are, again, a little bit harder to understand, perhaps, but they can be extremely useful because we can use them to make outliers less pronounced if we have outliers that are extremely large values. This isn't a transformation that's going to help if we have outliers that are extremely small values, something like really large negative values or values that are really close to zero. If that's where the outliers in our distribution are, a log transformation is not going to help. But in a case like income, where we often have outliers that are really large values, we often use a logarithmic transformation to lessen the effect of those outliers. And we'll see an example of that graphically in just a moment. But again, outliers are important to deal with because, like we talked about in part one, outliers can have a really big effect on the mean. And the mean is not the only statistic that outliers can have a really big effect on. We'll also learn later outliers can have a really big effect on regression. So, logarithmic transformation is one way that we can make it so that outliers aren't having such a big effect on the mean, on a regression, something like that. So, that's part of why this is such a useful transformation to be able to have in our toolkit. Um, There are pros and cons, though, with log transforming a variable. Even though log transforming or logging a variable is going to help lessen the effect of outliers, logged variables are going to be harder to interpret. The units are not going to be as obvious to interpret. So that's a downside of doing a log transformation. Again, salary data is a good candidate for log transformation because we often have big outliers on the right side of the distribution, meaning extremely large values. So here's an example of a distribution. We're still looking at that same data set of Texas school districts. But now, instead of looking at the turnover rate, we're looking at what is the average teacher salary in that school district. So you can see that the typical school district had an average teacher salary of around $50,000 a year. Um, but there's quite a bit of variance, right? Some school districts are only paying an average of around $40,000 a year, even a little bit less. Some are paying as much as $60,000 a year. But we have a few districts that are outliers on the right side of the distribution, meaning unusually large values. It's not a lot of districts, but you can see there's tiny little bars here closer to $70,000. One school district or more that even seems like they're getting closer to $90,000 as the average salary in that district. And we don't see the same kinds of outliers here at the lower end of the distribution in terms of there aren't really any unusually small values, right? There's nothing out on this end of the distribution. Instead, it seems like if we have any outliers, they're on the right side of the distribution. They're these large values. And that means that this could be a good candidate for a variable that we might want to use a log transformation with. So, what happens when we log transform this data? Well, here is that same data after a log transformation. And you can see now the units on the y-axis don't make a ton of sense intuitively, right? Because now we can't just interpret this as, how many $1,000 a person makes per year. Instead, we would have to, get out our calculators or something in order to be able to figure out what a 10.6 on the log scale is. So we don't need to worry about that right now. What I want to focus on is the shape of the distribution. And it's a little bit hard to compare these two graphs, but these are our large outliers, right? Our right side outliers. And you can see that they've moved in, arguably, a little bit closer to the main part of the distribution in this second graph. It's not super obvious that this has made a big difference just visually, but in fact, we have lessened how extreme these right side outliers look now. And that's going to be much more obvious if we actually look directly at the mean for these two different versions of the variable as opposed to just looking for visual evidence. So remember, I said that the mean is very sensitive to outliers. And in this case, this is the just the raw teacher salary data. What is the average teacher salary in each district? And you can see that the mean is 47,000. If we round to the nearest 10 or the nearest thousand, we would say $48,000, while the median, this is showing the percentiles, and the 50th percentile is equal to the median. The median, if we round to the nearest thousand, is $47,000. So $48,000 is the mean, $47,000 is the median. So a $1,000 difference, not huge, but something between the mean and the median. And one of the main differences we said between the mean and the median is that the mean is going to be more affected by outliers. In this case, the outliers we have in mind are those unusually large observations at the right end of the distribution, right? The districts that are spending somewhere around $90,000 on average per teacher in salary, or maybe these ones as well, closer to $70,000. So that's what is going to be dragging this away. But after we do a log transformation, what we're going to see is that now the mean and the median look very similar. It's a little bit hard to say exactly how big this difference is because now we're looking at different units, but here 10.77, if we round, is the mean versus 10.75. So a zero point zero 0.02 difference, again, hard to say exactly what that means, maybe about 2% if we use a rule of thumb that's sometimes used to interpret log transformed variables, but not a huge difference there. And we'll come back to that rule of thumb in just a moment. So here is an explanation of some of those rules of thumb. Basically, if we think about comparing or making a change in our logarithmic scale, we can interpret that as similar to a percentage change if we move the decimal place over two places. So in other words, if a teacher log salary goes from 10.5 to 10.6, that's a zero point 0.1 increase, which we can interpret as approximately a 10% increase in the salary. So feel free to play around with this rule of thumb more on your own if you're curious about it. It's not going to be a major focus of how I approach this class. So we're not going to go through as much detail on this slide as we have in most of the others. And I will also link in the notes to this video to a textbook by Whelan, which has a nice example in one of the chapters about using log transformations to help us get to a percentage term kind of interpretation of wage gaps by race.